This is the third and final video in the Chapter 3.4 Linear Programming lesson. You are instructed to attempt the linear programming problem at the bottom of the page, and there is also work for you to show, or a spot for you to show your work on the next page. And so I'm going to go through the solution to that. So it said a small community is trying to establish a public transportation system made up of large and small buses. The community can spend no more than $180,000 for the buses and no more than $1,200 per month for maintenance. So those are going to be our constraints right there. The total amount for buses and the amount for maintenance. A small bus costs $10,000 and can be maintained for $75 per month, and a large bus costs $20,000 and can be maintained for $100 per month. So I'm going to just work with this paragraph and ignore the one that's blocked in blue. First of all, you define your unknowns. Your unknowns are the number of small buses and the number of large buses that the community can establish. And now we're going to make our constraints. There were two constraints talked about in the first paragraph: cost of the buses and cost of maintenance. So I wrote my cost of the buses is 10,000 x plus 20,000 y is less than or equal to 180,000, and simplify that. All three of those are divisible by 10,000. So I get x plus 2y is less than or equal to 18. So that's the one I'm going to graph right there. And then the cost of maintenance per month is 75x plus 100y is less than or equal to 1,200. All this was pulled from the first paragraph. All these are divisible by 25, so I divide everything by 25, and I get 3x plus 4y is less than or equal to 48. And that's the other constraint I'm going to graph. The number of buses has to be positive, so these constraints are x is greater than or equal to 0 and y is greater than or equal to 0. So now you're going to graph the feasible region and identify the vertices. So you can see I have graphed the red and the shading is below that, and I've graphed the green and the shading is below that, and the feasible region is where the shading overlaps. So that's where I've highlighted in yellow. Any point coordinate in this area satisfies those two constraints. So the community can purchase any combination of small and large buses in this area and it'll satisfy their constraint. However, they're looking to maximize the number of passengers, so that's where we get to our objective function. So now we're going to, before we do that, let's just make sure we have the feasible region vertices. So they are 0, 0, that one's easy to see. 16, 0, that one's easy because that's a x-intercept. 0, 9, that's also easy because it's an intercept. So the one that we have to verify is this one, 12, 0. So we have to make sure that 12, 0 is indeed the other vertice. We can't just guess, so we have to verify it. And I'm verifying it here. So I've written the two equations. I multiplied the top equation by -3. I solve this using elimination. I get y is 3. That's what I was hoping for. I plug it back in and I get x is 12. So indeed this point right here is 12, 3. But you can't just guess. You have to show that indeed that is it. So now we're going to write our objective function, and that's what's given in this second paragraph. Each large bus can carry up to 15 passengers. Well, large is y, so that would be 15y. And each small bus can carry up to 7 passengers, so that would be 7x. So our objective function would be 7x plus 15y. Pretty easy. So I'm going to write that down here. P is the number of passengers, and our objective function is 7x plus 15y. This is what we're trying to maximize, the number of passengers. So now you evaluate the objective function at each vertice. So we're simply going to put in the corner points for each one, and we're going to figure out the number of people each combination can hold. Obviously, if you have 0 buses, you're going to be able to hold 0 people. So for the second constraint, 16, 0, they would be able to hold 135, pretty good amount. For the third constraint, that's incorrect, you guys. That should be 112. For 09, that one would be 135. 15 times 9 is 135. And for 12.3, that would be 129. So the maximum occurs here at 135. So the maximum number of people we could hold is 135 if we purchase 0 small vans and 9 large vans. So the last thing we do is we write our solution sentence. To maximize the number of passengers, the community should purchase 0 small buses and 9 large buses. Hopefully you got that. We'll talk about questions you might have had, and we'll be working on the problem set next class. Make sure you bring graph paper. Thank you.